And again, welcome to the tutorial in a time like week 6, where everyone's having midterms and is super busy. And this is going to be quite informal. This is going to be laid back. It's going to be pretty casual, and but it's still going to be somewhat technical. So I'd say stay prepared, and let's get going. All right. So I divided this tutorial into 2 major parts. The first one, I'll just talk to a PPT slide like I'm doing right now. And for the second one, I think we could actually start and write a little bit of code. Ben, can you mute yourself? All right, thank you. So first part, the introduction, is rather uninteresting, really. It's just something about me. And then we'll go and demystify the game engines. It's literally just code. It is a loop. It is a while true loop running on the main function. So yeah, it's just a sparkling main loop. It is nothing other than a usual piece of user software. If anything, scripting in the game engine itself might be more unorthodox than the game engine itself. And then we'll take our first step in game engine development. And we're going to start by trying to build a blank window in the Windows operating system and see if we can go anywhere further. And that's just the plan for today. All right. First one, self-introduction. As you probably know, I've been in the studio for a while, and I've been doing game development for a while as well. So I'm Xiao, and I'm a 3rd-year math of computation major, but I'm graduating in 3 years, so which means I'm basically a senior now. And I interned at Huawei in my first year, and I went to TikTok in my 2nd year. It was a rather unpleasant experience at TikTok, but it's fine. And I'm now working professionally in game development at Uncapped Game Studios, which is led by the ex-Blizzard StarCraft 2 veterans. We're building a real-time strategy game. And well, now I get paid doing game development, which feels good. All right, that's all about me. Now let's talk about game engines. What are they? What do we typically talk about when we talk about game engine? What sort of engines does everyone here use? I'd imagine Unity, because that is Unity is pretty friendly towards beginners, and it's pretty easy to find your footing in the scripting world of Unity. And yeah, what else? Do you guys use something like Unreal, Godot, maybe?
I tried a little bit with Unreal this past winter break, and it looks pretty interesting, but I think there's a whole lot to learn, but really interested in learning that.
Yeah, I can definitely see that. Unreal relies on C++ as scripting, or maybe the blueprint, and which is a sort of like a code generation tool, which makes things a bit harder at times. And but on the visual side, Unreal have a lot of stuff built in, which makes pretty good looking graphics without too much from the content creator side. Well, it still requires a bit, but that's Scratch. Oh yeah, Scratch. Scratch is it's a lot of people got into programming with Scratch, which is pretty nice. And Scratch is definitely sort of the visual programming thing, where you just try to drag the blocks around and assemble the logic from the blocks. A lot of the commercial, not necessarily commercial, but in-house game engines in some of the AAA studios, something like Triart or Infinity Ward, have some similar technology where the designers just use the visual programming, something like Scratch, or maybe a node-based approach, like the ones you do in Blender and Unity when you are dealing with shaders to create a gameplay logic. Yeah, that's definitely a good example of game engine as well. So, well, engines don't always exist. There are a period in computer science history where we don't have game engines at all because they haven't been built yet. So before engines, people still do games. But how do they do games without an engine? Can you imagine writing like a game starting from scratch without Unity? It's gonna be it doesn't sound very pleasant, but well, here we go. We have something like a Rogue, which is way before game engine. Yeah. As you can say, this scene probably just like runs on Rogue probably doesn't have an engine. Well, it doesn't. And it is solely written from scratch. If any of you have taken the course CS32 at UCLA, you might have, I mean, I think every professor gives an assignment on running a video game from scratch to teach you about object-oriented programming, right? So you have probably written something on your own, which is a video game, but without an engine. Or maybe there's skeleton code. I don't know. I don't know how. What's the project for CS32 for you guys? For me, it was Rogue. Yeah.
I think we had some kind of zombie car game where you're supposed to like dodge stuff with your car and like shoot zombies.
Oh, nice, nice. Yeah, yeah. Like they often do like game development in CS32 just to show people how to do object-oriented approach to programming. And now we have we live in a completely different world where everyone, their mom and their dog has access to modern commercial game engines. They are not just commercial ones. There are plenty of in-house solutions. I think Blizzard Team 1 and Team 2 use the legacy one from something like Warcraft 3, and Call of Duty has its own solution, and a lot of the AAA studios, especially like the console first-party ones, have a lot of their own stuff, which which you only get to see when you work there, and it is on a strict NDA, so not a whole lot of people hear about it. And there's also like a Frostbite from EA, which is used in a lot of AAA titles, and in some people's opinion, it's being pushed way too hard at EA, so people just jump ship to Unreal there. So yeah, there are a lot of solutions, and nowadays we have the game engine take care of some common parts of our game and only focus on those that we need the most. For example, gameplay. Gameplay changes game by game. It is pretty hard to abstract out the common parts of gameplay. So people still do a lot of gameplay by hand instead of relying on the game engine. But say we have something like graphics or physics. Almost every video game, no matter what genre, even if you are doing a text-based game, relies on graphics, right? You have to see what's on the screen. You have to output a screen buffer. You have to show the user what is on the screen, even if it is just text. It is still graphics. So it is so common to video games that 99% of video games have to have some sort of graphics, which makes it a perfect candidate to be abstracted out and written once, run everywhere. So that is that would be the purpose of commercial game engines, that we don't want to reinvent the wheels. We want to take the wheels and use them. Hence, we get something like a graphics, physics out, and just package them into a solution, and everyone can use it. So here's a very rough architecture mockup. I believe that is coming out of the book Game Engine Architecture, written by someone who was from Naughty Dog, who I think worked on Uncharted, right? That is the flagship, or used to be the flagship title of Naughty Dog, the Sony first-party studio. And we can see there's a lot of components. Some of them present in 100% of the game engines. Some of them not so much. We have something like games specific rendering, which might not be in every game. For example, a game-specific rendering for real-time strategy differs wildly from that of an open world title. If I want to make Zelda, I need to see how I could display objects far, far away in like the opposite mountain. But if I'm going to make Rainbow Six Siege, for example, where I just shoot guns in indoor environment, I'll be less constrained about my draw distance, but more on the level of detail of everything surrounding me. And the top part is game specific, and the further we go down, the more in general, the more common the thing is, and the more it is close to the metal or the hardware that is actually running it. We build layers upon layers upon layers of abstraction to help our lives, to make our lives easier. For example, we have the drivers. Well, that is not a part of game engine. We don't write this. Those help us talk with the actual hardware themselves. And building on the drivers, we can have something like a hardware abstraction layer, which helps us run our game no matter which platform it runs on. For example, I have two different abstraction layer, one adapting my title to PlayStation, or another adapting my title to Xbox, so that I could ship my game on those platforms without modifying the upper layer. So I could concentrate on just doing good gameplay code. While I'm a good gameplay programmer and have the engine programmer pour the game everywhere by using layers of abstractions. I have picked some of the main topics that is common to a lot of game engines. So as I talked before, we have graphics. The engine needs to render the scene in a very short time interval. Modern PC games typically run at 60 to 144 frames per second. And if you are looking at something like last generation PC or console, they often run 30 frames a second. That is something like 30, 60 milliseconds per frame, which is not a whole lot when you think about it. It is a real-time system. We have to consistently output this many frames, which means the code needs to perform well. Otherwise, the game lags. We have physics. A lot of when trying to program in Unity, you have probably encountered something like collider box and rigid body. The collision and rigid body physics are two prime examples of physics that a lot of the game use. And of course, there's something like ragdolls or something like 2D physics, which is focused on just handling the box, the 2D box colliding into each other. And we have the audio, which is super overlooked. A lot of the independent game developers didn't bother putting good quality audio, and they don't appreciate the level of complexity behind the audio programming. For example, I think in many of the student-run studios, people don't necessarily put in a lot of effort in audio, which is understandable. And although often very overlooked, audio makes a huge part of the experience. A lot of the AAA titles relies on the audio cues to hint player what's going on and to make things very intuitive. Tell the player if the door can be opened or not by just sending out a sound cue. They have the background music, which builds up the atmosphere, and there are also a lot of technicalities in implementing audio system, which people often relies on third-party middleware. So that is a pretty interesting topic. If you are interested in audio programming, there are a lot of resources on that as well. And last but not least, gameplay. Have you ever thought of why you could write C# in Unity? Although Unity is not itself written in C#, Unity itself is written in C++. Yeah. Have you ever wondered, like, or kind of guessed why you could write C# in Unity? All right. So basically, Unity has something called a runtime, which handles the actual execution of the .NET code, the C# code you put in a script. Unity has something like a runtime, a small engine within an engine that takes the C# script you write and actually find ways to execute them to to apply the script effects to the game. So yeah, there's a lot of the runtime scripting support for gameplay system in many commercial engines as well. Unity uses C#, as far as I know. Godot has its own scripting language, and Unreal has something like Blueprint and code generation. So many engines support at least one scripting language runtime. All right, so that is the bird's eye view on the game engine systems. Do you have any questions before I move on to the code? All right, thank you. Sounds good. Let's take a look at what we have here then. So I'm here on the Studio Advanced Tutorials page, which you could find on GitHub. Yes. So if you take a look at this GitHub repository, does everyone know how to clone a repository here? So basically, you take the URL, and if you have Git installed on your PC, just make an empty directory. Oh, thank you. All right, see ya. Bye-bye. So say you create a new folder, and then you could clone a repository here by using the command line git clone with the URL, and it should handle everything for you. But just like this. Now I have a copy of the code. Let's see what it actually does. Going to the game engine fundamentals, you could see a solution called a triangular. I don't know why I named it triangular, probably because everyone starts with drawing a simple triangle. But anyways, we could open up the solution with Visual Studio, and then we could see the internal layout. This one is from a more advanced branch, which I'll roll back to, which I'll roll back into the main branch and have everyone start from scratch, which is a lot easier to follow. I just check out main, reload everything, make sure I have the latest version. Oh, I think you could do both. So if you want to try it right now, you could clone this and follow along with any text editor that you have installed on your computer. But if you want to try, but you could not be able to build a solution because it relies on the Windows API. The reason why it is on Windows is because a huge proportion of PC gaming nowadays happens on Windows. It just so happens to be one of the most popular PC gaming platform. So yeah, and in my opinion, DirectX is a very good API. It is super beginner friendly, and it has a lot of the smart pointer support, so you could write a more object-oriented code, which is probably a bit easier to understand for the beginners first trying out graphics programming and game engine development. All right, I have recorded a few clips on these topics, and I'll be playing them. And I did the voiceover for the first 4 of them, I think. But for the last one, I'll just have to pause and see if there's something that I could elaborate on. All right. Let's try. Hello again, my fellow engine programmers, and welcome to the code. Right now. So, sounds good. It's working. Hello again, my fellow engine programmers, and welcome to the code. So, this is where it all begins. This is the main function, or vmain function, because it is a Windows 32 exclusive signature. It is very similar to the other main function you find on, for example, something like Linux, where it is just called main, and it is the starting point of our entire program. When you're trying to script in a commercial game engine, for example, Unity, you're trying to write C# in Unity, you might have noticed that you never get to write the main function. You never get to write the starting point. And that is because the engine takes care of it for you. On a very high level, most commercial game engines can be thought of a while loop. Well, probably not this one. While true do nothing. This doesn't seem right. Alright, I'm going to zoom in a little bit. Well, one major difference between this piece of code and a commercial full-featured game engine is, while it is true, the game engine does something in here. And yeah, let's run this code, this main code, and see what it already produced from this very rough 60-line skeleton. Let it compile. It shows a window, an empty one, which is labeled the first game engine window. It doesn't do anything at all, because while true, we do nothing. If we try to click on it, it doesn't respond at all. It seems kinda dead. We couldn't even drag it around or close it with the little X on the upper right corner. The only way we could exit is by clicking the Stop Debugging button from Visual Studio. Right, so that is our starting point. An empty, mostly empty main function that does nothing. What if I rename this one to main? It will probably still compile, actually. Let's see if it does. I'm pretty curious. Does not. Well, it does not. Well, fine. Go back. We main. Whatever. We have an unresponsive window that actually does nothing. So what's in there? You might be curious. What is all of those code? It's super hard to read. It's super confusing. It reeks of the legacy APIs. It even has Hungarian naming. Now that we know we have our starting point, a main function on Windows, let's take a look at what it actually does. How do we write a code to display even a simple minimalistic window onto the screen that actually does nothing right now? But how do we actually do it? So first, we define a class name in the form of a wide character string. Why a wide character, you say? What is the difference between a wide character and just a simple character? Well, on Windows, a wide character is twice as long as a character, which enables so many options for localization. If you are from an international background, you may notice that Windows 10 supports more than one language. You might have Windows 10 running on Chinese, on Japanese, on many other languages, and the underlying string encoding is makes all of the localization possible, and Windows enforces a quite strict wide character interface on most of its public APIs, such as the class names and most strings. And then, after we have a class name that we know and love, we could change it to anything really. If we want to call our first engine a burger, let's do it. See if it compiles. It shows the exact same thing. And let's register the class to the operating system. Windows keeps track of all the window class that you register to. And once you have registered some of the properties of a Windows class, you could then use the window class to create actual windows. It's like when you have a prefab in Unity. You could drag the prefab into the editor and have it spawn a game object for you. Same deal. To do that, we need a recipe. And our recipe is called a window class EX struct. Yes, it is a struct. We're passing in the struct to the register class EX function. And the struct contains a lot of stuff that we don't care about. But what we do care about is the long pointer to the class name, which we just defined as burger. Well, maybe my first engine. Well, it works too. and a long pointer function to Windows procedure, which we define as our custom window procedure. Let's not worry about it now and come back to it later. Notice how the naming of the stuff in the struct is a little bit strange. It is because when Windows 32 API first was constructed, well, the IDEs are not as developed as today's modern stuff like Visual Studio. So people used something called a Hungarian naming scheme, where they put the type of the stuff in front of actual variable names. And it made everything super confusing and super hard to read. I strongly recommend against writing Hungarian notation in year 2022. For example, we have something like a long pointer to something, a long pointer function to something, and so on. All right, once we have filled in the recipe, we then use it to register our class. That is a very common practice among the legacy Windows 32 APIs. You try to write out, because like if you pass them all in with parameters, there would be too many parameters. So what they do instead is that they have a struct that act as a recipe, and you fill in the struct every field and just pass the entire struct in, so that the interface, at least when you are trying to pass in stuff, it looks relatively okay. And you could gradually build up the recipe step by step in a builder pattern. That is also one of the advantage of using this kind of approach. After the class is registered to the operating system, we then try to create such a class and show the class to the user. What if we try to register a class with under one name and try to actually create a class that has a name that doesn't match what we registered? For example, we created my first engine, and now we're trying to create a Windows from Burger. What happens is that you don't get a window. The names must match. And we could call our window whatever we want. That is completely decoupled from the underlying class name. For example, if we want to call our window pizza, as it shows to the user, we just name it so. And here we go. The window is now called a pizza. We are trying to create a fixed size window here where the width and height is predefined in the code as constant values. So if we, instead of 16 by 9, if we want something more like a square, we could easily do that by changing the hard-coded values and recompile like this. But what if we create a window and don't show the window to the user? Well, it is not going to appear on the screen, because what exactly happens is that when we try to create Windows, when we try to call the API create window, what we actually get is a HWND, a handle to a window, which I call window handle here, and it is an abstract thing. We need to put it on to our screen buffer. We need to tell Windows, show this one to the user by calling show window function. And if we just comment out the show window function, naturally, it doesn't show on the screen at all. All right, so now you have it. This is all about what the existing code does. And now something to make it better. We have a window that doesn't accept any user input at all. We want to change that now, and we want to build something that helps us actually respond to the user message and do something on its own. So what we are going to do is that we are going to construct what is known a message pump. We're in a while true loop, or just like a while loop in general. We repeatedly check for the message that the user sent us. And luckily, the operating system Windows maintains a message queue for us. So we only have to peek at the message queue every now and then and see what happens. Well, but first, I will be jumping onto another project that I wrote earlier. It's another game engine project that is written from scratch, just like this test project. And yeah, and I'll be looking at some existing stuff that I wrote and trying to port the code into this example and see how it does. Before we write our main loop ourselves in our new project, starting from scratch, let me show you something else. This is called Geothermal. This is my hobby project, a game engine that I've been working on in the past half a year, and it is on GitHub, completely open source, and so far it is maintained by me myself. And yeah, it is a it is certainly a better game engine than what we have here, but it is still a super early prototype. It have some sort of overall shapes, which you can see. Let me do a clean compilation and see how this game engine works compared to what we have here. It does seem pretty broken just because I did some sample stuff. I have some sample modeling here. So you can see it has a 3D scene. It has a window that I could use to display my graphics. And I could move freely in it. I have some GUI on the upper left corner tell me where I am and what are my camera angles. I could reset the camera. I could toggle debug mode where it draws the bounding box for each geometry in the scene. And yeah, it does look a bit more complicated than what we have here in our engine, but if you look at the Vim main function, you can see it runs under the exact same principle. I have a class name, and I use it to register my Windows class, but only this time, I package it a little bit so that it doesn't look so messy in the main function. I have my fixed size window initialized from a set of constant. I show the window to the user, but under here, that is where things get different. I initialized a lot of stuff. For example, my device resource. So if you see here, there's something called a Std Shared Pointer, which is just a smart pointer which manages our memory smartly, so we don't have to worry about manually freeing stuff. The make shared function conceptually is a lot like the new function which you are given in C++, but this time you don't have to delete it. It is managed by itself. Resources or a rendering context from the DirectX API, and which is something that I use to keep track of the state of the renderer and draw stuff onto the screen. I set the window for my device resources, and I initialized the main game loop with our device resources. I also set up the GUI, and then the while loop actually happens in this function, in the run function. From the GameMain.instance, I run my infinite loop like this. I try to take the message from the user, try to take the input from the user and see what exactly do they mean. When the window is not closed, I repeat. All right, thank you, Christian. See you. Immediately take message out from the message queue associated with my window, and then I try to do stuff accordingly. Just like there's an update function every frame in Unity, I do have an update function as well in the main loop of the game, where I update each game object and render the entire scene from my render pipeline. As you can see, this is the logical flow. Where in the main function, I set up the window, I set up the resource that I need to use in my main loop, and I simply run a game. When the game is exited, I will have the result. I clean up the GUI and then exit with the result. The bulk of the while loop happens in the run function, where I process the message and update the state of the game accordingly. And where do I render the entire scene? Here, render pipeline, render. So that's a little bit of stuff from my previous project. And I intend to carry on this piece of code and try to port the main game loop, which is just a while loop with added stuff. Every game engine, well, not every game engine, most game engine is a while loop. Yeah, that is basically what game engines are. They are while loops in the main functions that take care of a lot of stuff and offers you a lot of functionalities. But at the end of the day, they are while loops. Game engines are while loops in the main functions. All right. Now, before we start, some logistics to make our lives a lot easier. ACM Studio is using Git to do the version control for most of the projects. So first, I like to check if I have made any change already. Well, yeah, it does seem I have a few lines of change in the vmin.cpp, so let's save a checkpoint. Let's just call it empty window, so that I know I could always get back to it whenever I want. Let's try to see it in the log. Yes, we do have the empty window here as a commit, and I can reset back to this hash whenever I mess something up. And now, let's take the entire thing onto a feature branch. Well, this didn't quite work. Oh, git checkout. All right. Let's see. Yes, we are indeed on our feature branch. Now we are all set and we are ready to start working. If we don't want to write everything into the Vmin file, let's open up a new abstraction. In this case, let's just make it into a class that we call a game engine and create the files accordingly. First, the header. You can also right-click on the filter in Visual Studio and create file. Or alternatively, if you want to, if you are very familiar with advanced build system, you could also manually create a file and regenerate the solution as well. So whatever you choose, just use your preferred way to add in some file to the solution. Should be good. Just call it engine. Engine.h. Pragma ones, which act as the compilation guard, and we might still need some Windows stuff in there. A class engine, and we will use this as our overall abstraction in the following tutorial. We will create a C++ file accordingly. Include a header. Include a header in the Vmin as well. Initialize our engine right after showing the window. And now we're all set. Does it compile? Happy to find out. Yes, it does. Now all we have to do is design and implement some functions in the engine class and spin it up, have it output some sort of graphics, and find a way to take input so that window is not unresponsible. All right. So the next step would be from here to here, where we have a working window that does something. It actually does something. It has the engine object that we just created in and initialized, runs some sort of game main loop. So I will put together a time lapse that shows how I migrated a lot of the message pump features from my previous project to this one. And then I will start go over line by line on what exactly is happening under the hood. And just remember, there's no magic. Everything you see is just nothing but C++, which is calling some sort of a Windows API from provided by the operating system. We are just starting from scratch. There are only 3 files. Actually, I'll just, it belongs in source file, not a resource. We have 3 files, engine.h, engine.cpp, and vmin.cpp. That is all we have, and that is all we need to do this. And once we have designed and implemented some basic functionalities in the main loop, now we have a window that we could drag it around, we could minimize it using the button. We could also even see that the window tells us that it is drawing something. Well, it is not, that it pretends that it is. And once it stops pretending and actually draw something, we have our first triangle. And from the first triangle, remember every geometry, most geometry that you see in the games now is based on polygon rasterization. So once you draw a single triangle, you can start building complex geometries by combining the triangles together, and you could find ways to shade the triangles by implementing shaders, and then you have everything you need, and you could you are basically working in a full-featured, a basic, not necessarily full-featured, a basic renderer once you get to that point. Just like what I have in my other project, which is simply rendering some geometry and have the player control some of the logic in the game. So just to show it again, recompile, run, and heavy loading time just because the geometry that I tend to use in the demo. And yeah, that is entirely written in C++ and entirely written by myself with the help of with just the basic interface given by the operating system. And everyone can do that. Game programming, engine programming is not magic. It is just code, and it is very intuitive. It is just a piece of a user software. So if you don't take away anything at all from the code section, just remember that no matter how complicated a game engine seems, it is always just code. It is always just software, just like everything else. So that is the point that I want to get across. Game engine is just code. It's just code. It's nothing else. So let's do the time lapse, and I'll talk about what is going on after playing this one. Okay. Or I could talk over it. First, I do a checkpoint in Git because I don't want to lose my progress, and I commit very often, one step at a time, so that if anything goes wrong, just do a hard reset. Now, let's check. We have the engine. We want to initialize the engine in case there is some potential resource that we want to put into the engine to have it work. For example, engine needs to know what graphic support are we using. Otherwise, how is the engine supposed to write to the screen if we don't even have if we don't even establish our communications with the graphics card or whatever device that is in charge of drawing, right? So I tend to explicitly initialize my engine as a public function. The reason that is that I know that it is ready to be used, and I don't really rely on constructor for a lot of things. Yeah. All right. The while loop goes into the engine. All right. Public methods, just the two that we just talked about. We want to initialize the engine, and we want to run the sparkling main loop, the while loop in the main function. That's what a game engine is. It is like my fifth time speaking about it, this tutorial, but yeah. And it's initialize main loop. Here we go. Wrong, sparkling main loop, just to make it fancy. Well, I didn't realize I made a typo, but anyways, yeah. This is literally what an engine does. So, well, it's a bit too fancy. Let's just call it main loop and create signatures for them, which I tend to just like have Visual Studio take care of. Now we have it. What's now? We don't really have anything to initialize. We don't have to, because we're just like, we are trying to do the message pump first and worry about drawing that triangle later. So, right. So let's just focus on the main loop, and we'll come back to initialization later and maybe see what could be done there. All right. The main loop is it's a while loop. Of course it is. What else could it be? Exclamation marks times 5. Okay. So this is a bit redundant, but I still tend to keep something like keep track if the window is closed, so that I could force to close the windows in the logic. So say I want to close the windows right here, right now. I don't want to see it anymore. Get rid of it. Goodbye. And I could just do it by setting that its window close equals to true and exit the loop. So that is the one of the purpose of this Boolean variable. It is of course initialized to false. All right. Nothing here. Nothing there. Yeah. We tend to initialize stuff explicitly. Yeah. At least here. I mean, most times I still use the constructor stuff. And start porting. The while loop looks a little bit like this. We have a message struct, which is also provided. The struct definition is provided by the Windows API. So Windows tells us how to receive a message in form of a struct. we have, so we create one such struct and zero initialize it in C++, which is like the curly bracket zero notation, which just initialize everything in the struct to be zero. Just fill it to the brim with zero, so that it is super clean. There's what could possibly go wrong, right? With zeros, yeah. And while the window is not closed, while we don't force close the window, it is typically, it is mostly just like a while true loop, where we just like lock in the infinite loop, where we check for the message from Windows. Where we use the API pick message to see if there's a user message in the incoming message queue. If there's not, well, we hit the boundary of the outer while loop, and we are still locked in the infinite loop, still trying to wait for the message, check for the message. If the user sends one, then the pick message returns something greater than zero. Now we know we have received a message, and we respond to the message. Of course, we handle the message by passing the message into the handle message function, and see what happens. And after that, we update. We are not necessarily after we translate the message we update. We always update every frame. So you can see that update and late update function is called in the outer while loop instead of the inner while loop. We don't want the update function to be triggered by user input. Say I move my mouse, it update. No, we don't want that. We want the game engine to update. We want the game engine to always update, no matter if there is or isn't any user input. So that is the reason for this particular loop. Nested while loop, a while loop within a while loop. All right, we have the buffer, the struct, and report our loop here. Well, the signature should be a wide parameter, which is a type defined by Windows. Yeah. We use it as a return value to see if the program has exited normally or if anything bad happens. And we could use these parameters as an indicator to see what exactly went wrong in the code, so that we have a much clearer understanding of why did my engine crash, instead of did my engine crash, or did someone close it, or did something unexpected happen where it just exited out of the loop somehow. Yeah, right. So that is the purpose of using a wide parameter here. Now we see Visual Studio is complaining that thing doesn't compile. But why? We don't have the handle message function implemented yet. Visual Studio couldn't find the signature for how you want to handle the message. So we need to pour that in as well. All right. Windows is complaining again. Visual Studio is complaining again because I have something that I don't have there. It's the GUI. I have the dependencies of a GUI library, which is called IMGUI, which I do not have from the clean project here on the Studio repository. So I mean, we are not at that stage where we need to consider about a GUI, so might as well just remove it. And all right, now something else, an input system. The way we receive the player input. For example, player taps something on the keyboard, a keystroke is sent to the window, right? So say I have a, let's just do this here. Go to the Geothermal, go to the game loop, and see how the input is registered. And no message right here. right? So I have an input system, which is itself a class that register the player input that captures that message. The message come in. If the message is one of those, for example, we press a key, the key is down, the key is up, the mouse button is down, the mouse button is up, or the mouse moves. Those are the things that we are trying to. Those are the things that we are concerned about. Those are the things that we need to know when we try to process the input. So right. So I just take the message from the message prompt and see, well, this is user input. Do things accordingly. So that is how we register the input in almost every game engine that you could find on the market. For example, like how does Unity know that your a key is down on your keyboard? How does Unity know that you moved your mouse? It's because your input action sends a message onto the window. Windows, the operating system, cache the message in the message queue. You look at the message queue, take out the message, and see here, you have it, the user input. So that is a part of it as well. So for now, our little bank project doesn't have anything like an input system. So what we do is just we pretend that we register the input, right? Just pretend. And return 0. We also translate the message and dispatch the message, which essentially, on a very high level, just tell Windows, the operating system, to do the default thing that Windows does without you overriding what Windows does. So it just tells Windows. So do you know how to handle the minimize? Do you know you should minimize the window when I click the button? Windows does that by default. You do that by default. All right, you go ahead, you do it. So that is essentially what we are telling Windows, and you just use the default stuff. We don't have the update or late update function right now because they are not implemented yet. And those are the gameplay system update ticks and late update ticks. So for now, we'll just remove them because we don't have a gameplay system yet. All we are trying to do is that in a nested while loop, we take the cached message that Windows the operating system cached and send us, and we process those messages by the default process. And now our Windows should be able to respond to basic things like closing, minimizing, and be dragged around, right? Those are the default things that Windows support. And change the signature. We keep track of the result where we exit and return the exit here. All right. Now we try to build the entire thing and see what happens. Well, before that, we pretend we are doing something. We pretend that we are trying to render something onto the screen. So we could just spit out something onto the console log and try to pretend that we are trying to draw something onto the screen. We could also pretend that we are trying to update the gameplay system and add in here, I guess. I'll create a signature for the implementation. That's nothing. Great. And render, maybe first update. After we update, we render. Just like this. Simple. Now we're just pretending, but we could very well implement those functions and to make our game engines actually renders and updates. Yeah. I think I went for outputting something onto the logs. Yeah, here. Great, draw something. Does it build? Yes, it does. Now we have a window. And if we take a look at the output, we see there's a lot of logs. And why is that? It's because we are sending out one message each frame. So it flooded the console. And it's a bit unfortunate. We don't want that. So we just send a message once, pretend we're doing something. Yeah. But that is also a good thing because you can see how it floods the console, which means it is indeed refreshing every frame and doing something every single frame. Let's just print the log exactly once and see if it behaves. Just trying to pretend it's rendering something. All right, wrong again. Output menu, draw something. It's working. We can drag the window around. We could close it. And it behaves just like a normal window would do. All right, checkpoint. Commit everything. And that is it. Basic engine class without graphics. Here we go. So yeah, this is where we are right now. A basic engine class without graphics. And we could then insert all kinds of stuff later into this code and maybe initialize the graphic resource according to the size of the window and the size of the screen, the refresh rate, the back buffer of the window, and create the back buffer swapping where we have two buffers that is swapped every frame to show the user our tiny flashy graphics. We could initialize graphics resource here and initialize with some type of resource. And then, of course, we could actually go into the render function and actually render stuff. Here, and instead of printing a whole bunch of logs. You could also have the gameplay system be updated in the update function. So question, how does Unity update every mono behavior each frame? They just do a for each loop here. For each game mono behavior, script that is in some collection script dot update, right? So in fact, this is all driven by the update function in the mainlet. It tells every mono behavior that, hey, it is time to update. It is time to start, to wake up, to do something. It is all managed by the game engine, right? This is simply how it works. Why does Unity have all those magic signatures where it just automatically works? Why does update got where does update even called? Did someone call? Did some higher being, an invisible god, call your update functions so that they run once every frame at the beginning of the frame? Obviously not. It is called by the game engine. The game engine manages the call of the script and the stuff so that they do something. This is just something starting from scratch. We have something like 60 lines of code in this one, 28, so roughly 100, roughly 165, under 200 lines of code. We have the general shape of a game engine. The rest we have to do is just to fill in the stuff, which is the fun part, and also pretty challenging. So yeah, all right. Initially, I was thinking maybe we could get to the point where we draw a window, which we just did, using the native Windows 32 API. We just did. It all comes from the header windows.h, which is just the default header that ships with any version of Windows. By any, I actually mean any. It ships with Windows like 95 2K. Yeah, like any version of Windows shipped with a Windows header, and you could use them to essentially tell the operating system what you want to do. It is super. It is not exactly close to Metal because there's a layer of operating system between you and the driver, but it is close enough for our purpose and for the purpose of most game developers. This is the lowest part that many people will ever venture to. The next step would be to initialize some sort of graphics API. There are many of them, not just DirectX. We have something like OpenGL, which if you have taken a course CS134A, they use WebGL. At least that is when I took the course, they use WebGL, which is a watered down version of OpenGL, which is pretty much the modern OpenGL is pretty much very similar to DirectX 11, which I happen to use as my graphics backend for my personal project here. The Geothermal project runs on DirectX 11, and now we have a lot other things like DX12, which is more modern but harder to use. We have Vulkan, which is very similar to DX12, so people just lump them together into a big category and call them modern API, I think. But some people call them Gen 12 API. So those two Gen 12 APIs. Close to the Metal. Hard. It's not easy to get started with graphics programming in Gen 12 API because there's so much things to consider compared to your good old OpenGL and DirectX 11, the 11th generation. Using one of the other, all right. Right, so if you want to start from scratch, I would say it depends on what you are trying to achieve. If you are trying to dissect what a modern contemporary commercial engine looks like, for example, Unity, you could start with the basic like 11th generation API like DX11 and OpenGL. Those are very powerful. The 12th generation API doesn't phase out the 11th generation API. They merely gives you a more advanced way to actually get more control of the actual hardware. So you could fine tune the performance by yourself. But for our purpose, for many modern games, 11th generation is it's quite adequate. It's enough. So now something you might want to consider is the cross-platform, where you can see that you could use OpenGL everywhere, practically on Mac, on Android, or maybe iOS. But DirectX is a Windows exclusive thing, at least by design. It is only available on the Windows platform. But of course, right? So you have something like performance, which we just talked about. They are all good. Even not even 11th generation is enough. It's good enough. Gen 12 gives you more control. And now we have compatibility. We're OpenGL Vulkan runs everywhere. EX is Windows only. And there's a huge factor which affects how you write and run the code, which is the API easy to use? How do we actually interface with the API? Let's show some example. I'll give you some bare bone code that is just based on DX11, very close to the graphics API itself, and see some of the flavor of graphics programming. Say I have bindables. Let's do a shader. Right. If you have taken the core CS174A, you might be aware that there are two types of shader. There's vertex shader that is drawn per geometry vertex. And there's also pixel shader or fragment shader, as people tend to call it in GL, WebGL, or OpenGL world, right? So, but how do you initialize and use those shader is by calling the interface provided by the graphics API themselves. So as you can see here, for vertex shader, I use the device resource, which is itself abstraction of ID3D11 device. It itself is a layer of abstraction on a graphics card. You can treat the ID3D11 device as a software representation of the graphics card, and ID3D11 device context as a software abstraction of what exactly is going on that graphics card. What are the states of my rendering? And now, given the abstraction of our graphics card and the state currently on the graphics card, we could try to initialize something like ID3D11 vertex shader by doing this stuff. We have a direct 3D blob, which runs, which is a structure that reads the code, that reads the shader code from our hard drive. And then we read file to blob, read the hard drive that actually contains the shader code, right? For example, date vertex shader, right? So it should look very similar to those you write in the CS174 class, right? So you got to write a shader, but did you ever consider how the shader is loaded onto the graphics card, how it is being represented in the software? It is nothing but code. It is all done by human. Like it is done by I think they use something like a tinygraphics.js framework, which they did the exact same thing. Well, maybe not exact, but roughly the same thing, where they initialize, read your shader from the string representation and compile the shader, send them onto the graphics card, and have the shader run on the graphics card, right? those are what actually happens behind the framework. If you are to write your framework yourself, you would be doing exactly what we are trying to do here, right? So we read the shader into the blob, and from the blob we create a vertex shader from the i3D from the direct 3D device, right? We tell the graphics card, hey, you come here. There's a bunch of strings, right? You take the strings, you create a shader for me. You just essentially compile it. Right? So we create a shader that is nothing but a software, nothing but maybe like a pointer to a struct that is in your memory right now, and we try to use it everywhere. We create a vertex shader. If the vertex layout is not equal to null pointer, we create an input layout as well. And when we use the shader, we bind it to the graphics pipeline. We bind the bindables to the graphics pipeline, so the GPU knows what should I use to render, right? The GPU is confused. What should which vertex shader should I use? So you bind a vertex shader to the GPU so that the GPU knows this is it. This is the vertex shader that I want to use, right? Yeah, and you just have the device resource. You use the rendering context. You use the ID3D11 device context. This one, this object here, you use it and you tell it, you bind the shader onto the pipeline so that it draws whatever you want. So, okay, that's a bit long-winded discussion there, but all I was trying to say is that you actually get to interface with the API if you ever want to write something like this. And it is a very crucial factor to consider if the API is very easy to use. You don't want to use an API which is hardly readable, or it has sort of the style that doesn't fit how you typically write your C++ code. In this respect, I'd say, again, 11th generation is easier because there is a higher level of abstraction. You really need to go too deep into the hardware, unlike in 12th generation, where a lot of you actually get to do a lot of fun things regarding the hardware layout. And another factor is that OpenGL is C style, whereas DX is more object oriented. So that's definitely another factor that you might want to consider, because as you can see from the DirectX 11 style, a lot of things can be considered as an object. For example, this vertex shader here, right? This one, this vertex shader, this D3D11 vertex shader, or the input layout, they could be considered as a more closely considered as an object, which is managed by a smart pointer. Whereas in OpenGL world, it is more like call a method and call another method and just call another method and so on and so on. So yeah, a lot of the style difference between the two camps, which you might want to consider. And is there anything else? Performance, compatibility, easy to use. I think that's the big three. Yeah, I think that's the big three. Yeah. All right. Any other questions? I know this is pretty technical, and it is probably a bit different from what we used to do in the studio. But yeah, if you find this stuff fun, you can just come work on your own project from scratch. and I could give your a few pointers on where to get started. Yeah, it's pretty fun. Yeah, it's actually pretty fun. All right.